All right, now this is truly your last video for AP Stats if you so decide to watch it, which I hope you do. We're going to look at 10 practice multiple choice questions, which are in the back of, not necessarily the back of your book, but in chapter 11, at the back of the chapter, there's the practice test. So I pull directly those 10 practice problems from. So let's discuss them. Number 1 says a chi-squared goodness of fit test is used to test whether a 0 to 9 spinner is fair. That is, the outcomes are all equally likely. The spinner is spun 100 times and the results are recorded. The degrees of freedom for this test. Oh. Well, there's two ways we did degrees of freedom for our three different kinds of chi-squared tests. We had number of groups minus 1, and we also had row minus 1 times column minus 1. Well, for a goodness of fit test, we specifically, if I can say that right, had to use this formula, number of groups minus 1. Now, how many groups do we have in this problem? You might initially say, oh, 9, because there's 9 numbers, but technically there are 10 numbers from 0 to 9. 0 is, if you want to call it, the 10th number. So we have 10 groups minus 1, so technically you have 9 degrees of freedom. Okay, and that is probably why they put 8 degrees of freedom as a choice, because you might look at 0 to 9, say it's 9, subtract 1, and get 8. Now, problems 2 and 3 use the same initial information here. Okay, so let's read through this. Recent revenue shortfalls in a Midwestern state led to a reduction in the state budget for higher education. To offset the reduction, the largest state university proposed a 25% tuition increase. It was determined that such an increase was needed simply to compensate for the lost support from the state. Separate random samples of 50 freshmen, 50 sophomores, 50 juniors, and 50 seniors from the university were asked whether or not they were strongly opposed to the increase, given that it was the minimum increase necessary to maintain the university's budget at current levels. The results are given in the following table. Which hypotheses would be appropriate for performing a chi-square test? Notice they don't tell you what kind of chi-square test. Now, obviously, this is not a goodness of fit test because we have a two-way table here. Now, we either have a test of homogeneity or a test of association. Now, the thing that stands out to me is this. Separate random samples. We have control over how many people go in each of our groups. And that specifically followed a test of homogeneity. Now, I mentioned in class that usually tests of homogeneity, you're doing some sort of experiment. In this case, this is one of those cases where they're not really doing an experiment here. In a test of homogeneity, there's also just one categorical variable. And that variable is year in college. Now, this isn't like a chi-square goodness of fit test where there's usually just one variable because we also have technically a second variable of yes or no. Okay, whether the treatment was good or the treatment was bad, that type of thing. And we can just have yes, no, whether they were strongly opposed to it or not. So if any of these talk about association, we know it must be wrong because this must be a test of homogeneity. So looking through these, I'm seeing down here, hey, association. Guess what? It's not that. Hey, this one uses the term independent and dependent, which is the same as association. So that's not it. Now the rest of these, I don't see the term association. So let's actually break these down. The null hypothesis is that the closer students get to graduation, the less likely they are to be opposed to tuition increases. The alternative is that how close students are to graduation makes no difference in their opinion. Okay. B, the null hypothesis is that the mean number of students who are strongly opposed is the same for each of the 4 years. The alternative is that the mean is different for at least 2 of the 4 years. Now this sounds pretty good, except there's one word that's causing it to be incorrect. Mean. These aren't mean numbers. These are counts of people. So this one bites the dust. Now, if we go back up to A, did anything sound a little fishy? And to me, the null hypothesis, with it saying already that the closer students get to graduation, the less likely they are to be opposed to tuition increases, it sounds like they're describing what they see in the actual data up here in our observations. Okay, they're describing a pattern. They're not describing whether, there's a difference or not. They're already kind of going into it. So to me, this doesn't sound right at all either, which leads us with C. So let's test it out. The null hypothesis is that the distribution of student opinion about the proposed tuition increase is the same for each of the 4 years at the university. So basically saying that the treatments are the same regardless, okay, where the treatments are year in college. The alternative is that the distribution is different for at least 2 of the 4 years. And this one is the legitimate one. So C is the answer to that. Now for 3, it asks the conditions for carrying out the chi-square test are separate random samples. Expected counts are large enough that they must be at least 5. And the samples themselves and the individual observations in each sample are independent. Which of the conditions is or are satisfied in this case? Now, the random part, it says separate random samples. So yeah, number 1, we're good, which means we can automatically cross out B and D. So this has a 1, this has a 1, this has a 1. We're good with 1. Expected counts are large enough. These aren't the expected counts, keep in mind. These are the observed. We're going to have to do either enter in this data into a matrix and then do the chi-square test command in the calculator, go back and look at matrix B, and then we can do that. Okay, so let's go to matrix A, edit. We have a 2 row by 4 column matrix, so a 2 by 4. And if I put in all these numbers, 39, 36, 29, 18, 11, 14, 21, 32, and then go to stat tests from the bottom, chi-square test, calculate. Who cares what all the chi-square and the p-value is? I just want to jump back to the matrices and go look at matrix B and scroll through it. So I'm seeing a 30.5, a 30.5, a 30.5, 19.5, 19.5, 19.5, 19.5. All of those are good. So it didn't take me that long to really check these expected counts were there. So 2 is legitimate. So now I know A is wrong. C is still looking legit, and E is still looking legit. The only difference between C and E now is going to be this third one. So the samples themselves and the individual observations in each sample are independent. Now typically we would check the population as at least 10 times the sample size. Or, as we have discovered, sometimes they want to know, are the samples themselves, really the individual observations in each sample, independent? Well, think about this. If you're considered a freshman, can you also be considered a sophomore, junior, or senior? No. If you're a sophomore, can you be considered a freshman, junior, senior? No. Same thing for juniors and same thing for seniors. So all of these people that are freshmen will be completely independent from all of these people who are considered sophomores, from those that are considered juniors, from those that are considered seniors. So 3 is met. So C bites the dust, and our correct answer is E. 4, 5, and 6 all use the same information here. So it says a random sample of traffic tickets given to motorists in a large city is examined. The tickets are classified according to the race of the driver. The results are summarized in the following table. So we got 69, 52, 18, and 9. So if I just add those up real quick, I want to get a total, let's say 69, 52, 18, and 9. It's 148 total tickets. Okay, the proportion of the city's population in each of the racial categories listed above is as follows. So this city has 55% white population, a 30% black population, an 8% Hispanic population, and a 7% other population. We wish to test the null hypothesis. The racial distribution of traffic tickets in the city is the same as the racial distribution of the city's population. So what they're saying there is, if 55% of the city are white people, then we should expect that 55% of all traffic tickets should go to white people. And if a city has 30% black people, then we would expect that 30% of all tickets given out are for black people. And if 8% of the people are Hispanic, we should expect 8% of tickets to go to Hispanic people, and the same thing with the other category. So 4 here says, assuming the null is true, the expected number of Hispanic drivers who would receive a ticket is, so this is a goodness of fit test. Okay, we only have really one row, and we do have 4 columns here. So the expected thing, a little different. This is where we have to use the percentages. And all we had to do was to take our observed count here. No, take it back. We had 148 tickets total, and we expect 8% of them to be to Hispanic people. So 148 total tickets, and then 8% of those, well, let's see, 0.08 times 148, we would expect 11.84 tickets to go to Hispanic out of 148. We actually saw 18, which is more than what we expected. So anyway, our answer here is D. Now, an interesting side note, the state of Illinois and all of its towns and counties, and even the state police, they keep track of this type of data. You can go online and look at, for example, these types of numbers for Collinsville. Okay, and there have been claims in the past that maybe certain cities pull over an unfair number of minority drivers, that they're kind of profiling them. And you can use the statistics of that data with a city's population distribution by ethnicity to potentially show that yes, maybe the cops in this town are unfairly pulling over more minority drivers than they are white drivers. So when I first saw this, I have seen this before. I have researched some of this data. Number 5 says, we compute the value of the chi-square to be 6.58. Assuming that the conditions for inference are met, the p-value of our test is... Now, if they were to give you the chi-squared, then all we have to do is use chi-square CDF in our calculator from 6.58 to infinity, degrees of freedom. We said this was a goodness of fit test. There are 4 groups. Groups minus 1 makes 3. So if I go to where normal CDF and TCDF was and scroll down a bit, my lower bound, 6.58, upper bound, infinity, 99999, 3 degrees of freedom, and I get an answer that is approximately 0.08656. Now, if I look at this, it doesn't give me exactly something like that, but it gives me some ranges. So I am in between 5 and 10%, so I am here at C. Now, you could have also put these numbers into list 1. You could have figured out what all the expected counts were into list 2, and then did the chi-square goodness of fit calculator command from there and gotten that same result. But really, I think it's faster just to automatically do this in your calculator. Number 6, the category that contributes the largest component to the chi-square statistic. So this is where we really will have to go and put all these numbers into list 1, and then list 2, we're going to have to put in all those expected numbers. Okay, so list 1, go to stat edit, clear out my lists here. So I'm going to do 69, 52, 18, and 9. Those are all my observed. List 2, remember we had 148 total tickets. So if we take 148 times each one of these decimals here and pop them up top. So we said earlier that this was 11.84. So, I mean, you could even punch this in into list 2. So that first entry, do 148 times 0.55, and it'll tell you it's 81.4. For the next one down, do 148 times 0.3. It's 44.4. We can, again, do the 148 times 0.08, and we get 11.84. 148 times 0.07, 10.36. So there's all of our expected counts. Now we can just go to stat tests. Remember, if you have the 83s that I gave you that special program in the program feature. So stat test, chi-square GOF test. Observed we put in list 1, expected I put in list 2, degrees of freedom we said there were 3. So if I calculate, and then that one list that was the CNTRB, those are your individual contributions. So scrolling through that list, I see 1.89, I see 1.30, I see 3.20, and 0.179. So who contributes the largest component? That would be our 3.20, which is for our Hispanic group. So it seems like Hispanics maybe are unfairly pulled over more than the other groups. 7 through 10 now, the last 4 problems, all deal again with the same piece of information. So it says all current carrying wires produce electromagnetic radiation, including the electrical wiring running into, through, and out of our homes. High frequency EM radiation is thought to be a cause of cancer. The lower frequencies associated with household current are generally assumed to be harmless. To investigate this, researchers visited the addresses of a random sample of children who had died of some form of cancer, leukemia, lymphoma, or some other type, and classified the wiring configuration outside the dwelling as either a high current configuration, HCC, or a low current configuration, LCC. Here are the data. Computer software was used to analyze the data. The output is given below. It includes the cell counts, some of the expected cell counts, and the value of the chi-square statistic. In the table, expected counts are printed below observed counts and are enclosed within parentheses. So for example, that's an expected, that's an expected, that's an expected, that's an expected. So they didn't give us these two guys here, which will probably show up in the next few problems, which is why they left them blank. So this problem says the appropriate degrees of freedom. Hey, perfect. Now we have a table, which means this is either a test of homogeneity or association, but both of them use the same degrees of freedom formula, which was rho minus 1 times column minus 1. We have 2 rows, our HCC and LCC, and we have our 3 columns, our different types of cancers here. So really we're talking about 2 times 1, which is 2 degrees of freedom. Number 8 says the expected count of cases with lymphoma in homes with an HCC. So again, that's one of the things that they left blank earlier. So here's HCC, lymphoma. That's for our 10 observed. How many would we have had expected? So this is where, to get your expected counts, you had to take the row total times the column total divided by the total total. So the row total, that's our 79. Column total, that's our 31. Divided by total total, our 215. They don't even really want to know what that number is. They just want to know how would you set it up. And hey, that would be C right there. And that's all it is. Number 9, which of the following may we conclude based on the test results? Okay, now they did give us a chi-square here, but they didn't give us a p-value associated with it. So if we real quick did chi-square CDF, 0.435 to infinity with, and earlier we said 2 degrees of freedom, let's see what kind of p-value we get from that. So 0.435 to infinity, 2 degrees of freedom, and we get a pretty big number here. 0.8045. So we would definitely fail to reject the null hypothesis. Okay, so if we fail to reject, we would say we do not have enough evidence to conclude, or at the alpha 0.05 level, to conclude that there, and our alternate would be, we want to show there's an association between the wiring and the cancer cases here. So again, our alternate would be, or our conclusion rather, would be we don't have enough evidence to conclude that there is an association. We just don't have it. We can't say that there's definitely not a connection, but based on our statistics, we don't have enough evidence to say that there is. So A, there is strong evidence of an association. Well, that we would say this if we had rejected the null hypothesis. If we'd gotten a teeny tiny p-value, we would say, yeah, there's a pretty good chance here that there really is an association. So this is saying the exact opposite of what we have here. HCC either causes cancer directly or is a major contributing factor to the development of cancer in children. Again, we said earlier we couldn't make an association, and this is saying that there is. They're implying it more here. Leukemia is the most common type of cancer among children. That isn't what we'd really conclude at all. I mean, if we look at leukemia, yeah, I mean, we got 136 cases versus 31 versus 48. Yeah, it's the most common type of cancer in this study. Is that something we would really come to a conclusion based on this data? No. This 0.8045 has nothing to do with that leukemia has the most. So that's a true piece of information, but not from the test results. There is not much evidence of an association between wiring configuration and the type of cancer that caused the deaths of children in this study. So there is not much evidence. That's pretty much saying we do not have enough evidence. And then we would have said of an association, and this is saying of an association. So this one's sounding pretty good. But let's double check and check E here. There is weak evidence that HCC causes cancer in children. Well, we're saying that we do have weak evidence here with our 0.8045 p-value. But we're not saying that this causes cancer. So this is too much of a stretch here. So the correct answer is D. And the last one. A type 1 error would occur if we conclude that. So let's review real quick. A type 1 error. This is when we reject the null hypothesis, but we shouldn't have. Okay? So in context now, we'll just throw this out of the way. We don't really need that. If we would have rejected the null hypothesis, we would have said, we believe there is an association, because that's what the alternate would say. But there really is not an association. So that's taking our definition and applying it a little bit more to what we're talking about here. So if I look for something very similar to that, neither one of these are really worded in that way. This is saying that it caused cancer when it really didn't. We're not trying to prove that things caused cancer. We're trying to show a link. Okay, we're not trying to, well, I'm trying to think of the whole phrase here. Causation versus association. Again, we're trying to show that things are linked, but not necessarily causing. That's what we're doing in our testing here. We're not directly pinpointing that this specifically causes that. All right? So we can't conclude that. And we also can't conclude that it didn't cause cancer when it actually did. Same thing. The whole causing thing is throwing that off. C, there is no association between the type of wiring and the form of cancer when there actually is. Well, that's really saying the exact opposite of what that is. This is really a type 2 error instead. So that's not it. D, there is an association between the type of wiring and the form of cancer when there really is no association. And that's exactly pretty much what I've got right there. So the answer is D. And that is all. That are your 10 questions. I hope you study up for your last test, and we will start to work on our portfolio projects for the rest of the school year. Adios.